Hi all, welcome to Heights to Fly. Today we are discussing about irrational numbers. What is an irrational number? Simply saying an irrational number is a number which is not rational. First we have to discuss about a rational number. A rational number is a number which is represented in the form of P by Q, where P and Q are integers, and the value of Q should not be equal to 0. What is a rational number? A rational number is a number which is written in the form of P by Q, where P and Q are integers and the value of Q should not be equal to 0. Then what is an irrational number? An irrational number is a number which cannot be written in the form of P by Q. Where P and Q are integers. And Q not equal to 0. The opposite of rational number. A number which cannot be written in the form of P by Q, where P and Q are integers and the value of Q should not be equal to 0. We can write examples as what is an example for rational number. For rational number, 2 by 3 minus 3 by 2, 3 by 2, then simply 5, where the denominator is 1, 5, etc. For a rational number, we can't represent P by Q. So the example is root 2, root 3, root 7 or root 5, etc. We can't represent these numbers in the form of P by Q. Another example is 5. Another root 2 divided by root 3. Another one, decimal numbers like non-terminating numbers which are not terminating, etc. Okay. Here we discussed about what is an irrational number, what are the examples for irrational numbers. Let's go to a theorem. The theorem states that let P be a prime number. If P divides a square, then P divides A, where A is a positive integer. Or let P be a prime number. If P divides A square, then P divides A, where A is a positive integer. It is a theorem used in further problems, mainly for further problems. So please try to understand it thoroughly. Let's go to the problem. According to prime factorization method, the prime factors of A, according to prime factorization, the prime factors of A are P is equal to, consider P1 into P2 into P3, etc. Pn, where P1, P2, etc. Pn are primes. Once again, we are factorizing the composite number, integer number A into P1 into P2 into P3, etc. Pn. In previous classes, we discussed about what is prime factorization and how a composite number can be represented in the form of prime factors. Here, A can be represented in the form of P1 into P2 into P3, etc. Pn, where these P1, P2, etc. are prime numbers. And we can rewrite A square in the form of P1, P2, P3, etc. Pn into P1, P2, P3, etc. Pn. Okay. In the state theorem itself, it is saying that P divides A square. P divides A square. Okay. According to fundamental theorem of arithmetic, we can say that A square have prime factors P1, P2, P3, etc. up to Pn. We say that A square is also have prime factors P1, P2 because A square is composed of numbers, prime factors P1, P2, P3, etc. Pn. But from the theorem, it is saying that P divides X square. So P is another factor of A square. So we can say that P is one of P1, P2, etc. Pn. P is one of P1, P2, etc. Pn because A square have prime factors P1, P2, etc. Pn. So we can say that P is one of the element of P1, P2, etc. Pn. Okay. Then what is A is equal to P1? Here we say that P is one of P1, P2, etc. Pn. Previously we say that A is equal to P1 into P2, etc. Pn. So we can say that P also divides A. P also divides A. Hence the theorem is proved. So again, first we state the theorem as let P be a prime number. If P divides A square, then P divides A where A is a positive integer. According to prime factorization method, prime factors of A consists of P1, P2, etc. Pn. So A square can be rewritten in the form of P1, P2. So you multiply it into 2 to form the square. Then according to fundamental theorem of arithmetic, A square is equal to the prime factors P1, P2, P3, etc. Pn. Already we say that P is one of the factors of A square. So P is one of P1, P2, etc. Pn. So we can say that A is equal to P1, P2, etc. Pn. Hence we can say that P also divides A. From this statement, we say that P also divides A. Hence the theorem is proved. That means we have to understand the theorem. Let P be a prime number. If P divides A square, then P also divides A. We are using this theorem in further examples. Then we are going to the next problem. Examination point of view, it is one important, and the theorem is root 2 is irrational. What? Root 2 is irrational. We are going to prove this theorem by a method, proof by contradiction. Proof by contradiction method. What is contradiction? That is, here the statement is root 2 is irrational, but its contradiction statement is root 2 is rational. So we state that root 2 is rational, then we prove finally it is a false statement. What? We are proving it by proof by contradiction. We take the contradiction statement of the theorem, that is root 2 is rational. Finally, we have to prove this statement is false. Okay. Let's go to the proof. Consider two integers. Consider two integers R and S. R and S. We can rewrite root 2 in the form of R and S, which is equal to root 2 where S not equal to 0. S should not be equal to 0. R divided by S is equal to root 2. And there is another condition. Suppose R and S have a common factor. If there is a common, which is a number other than 1. Consider the numbers, we can take two numbers R and S. R divided by S is equal to root 2. Suppose these numbers have a common factor other than 2, then we can simply divide these two numbers by using that common factor. Then we get the values A divided by B. When dividing the R and S using this common factor, we get the value A and B. So A divided B is equal to root 2, and A and B are co-primes. What? Co-primes. What is co-prime? Co-prime is also known as relatively prime, mutually prime, etc. And here we are saying that A and B are co-primes. We are discussing what is a co-prime number. A co-prime number is a number which does not have a common factor. That means A and B does not have a common factor. Examples are 14 and 15. It does not have a common factor other than 1. So this is a co-primes. Another example is 7 and 5. This does not have a common factor, so these are co-primes. Consider other two numbers which are 5 and 10. 5 and 10 are not co-primes because it have common factors 5 and 5. So 5 and 10 are not co-primes. Next, here we studied about what is a co-prime. A and B are co-primes. That is, they don't have any common factors. We can rewrite the value equation as A is equal to, cross multiply it, root 2b. A is equal to root 2b. We are taking the square. A square is equal to 2b. A square is equal to 2b square. A square, root 2 square, 2b square. Take the equation as first equation. In this statement, we can say that 2 divides a square. From this statement, we can say that 2 divides a square. From the previous theorem, we states that if P divides a square, then P divides A. From that, according to that theorem, we can say that from previous theorem, 2 also divides A. So it's one of the important statement. 2 divides A. Then if 2 divides A, we can write the value of A as A is equal to 2C, where C is an integer. Here we say that 2 divides A. So we can say that A is equal to 2C, where C is some integer. In equation 1, substitute this value 2. Substitute 2. We get, it is the equation 1, A square is equal to 2B square. We are substituting the value of A in equation 1. So 2C the whole square is equal to 2B square. As we said, we get 4C square is equal to 2B square. B square is equal to 4C square divided by 2. 4C square divided by 2, which is equal to 2C square. Here also we can say that 2 divides B square. So 2 divides b. Here b square is equal to 2c square. So hence we can say that 2 divides b square. 2 divides b square. According to the previous theorem, we can say that 2 divides b. This is the statement. Previously we say that 2 divides a. Here we say that 2 divides b. From these two statements, we can say that a and b have 2 as a common factor. Have 2 as a common factor. This is a contradiction. This is a contradiction for the first statement. This is the contradiction for the first statement. What was the first statement? Root 2 is rational. Therefore, we can say that root 2 is irrational. Root 2 is irrational. Why we say like that? A and b have 2 as a common factor. Here we say that by considering root 2 as rational, we say that a and b, a divided b is equal to root 2, where a and b are co-primes. They don't have any common factor. But finally we proved that a and b have 2 as a common factor. Hence this is a contradiction for the previous statements. So we can say that root 2 is irrational. Root 2 is irrational. Next question is similar question. Prove that root 3 is irrational. Root 3 is theorem. Root 3 is irrational. It is a similar question. Here also we are using the proof by contradiction method. Consider root 3 is rational, which is a contradiction statement of theorem. Root 3 is rational. We again rewrite the same. R divided by S is equal to root 3, where R and S are integers. Consider this have this have a common factor, so divide these values by that common factor, then we get a divided by b is equal to root 3, where a and b are co-primes. What is a co-prime? A and b does not have any common factor other than 1. Rewrite the equation as a is equal to b root 3. Take the square. A square is equal to 3b square. Take the equation as first equation. According to this statement, we can say that a square is completely divisible by 3, or 3 divides a square. From the first theorem, we can say that 3 also divides a. From the first theorem itself, we can say that 3 also divides a. Since 3 divides a, we can rewrite a in the form of a equal to 3c, where c is an integer. C is any integer. Taking the square, a square is equal to 9c square. A square is equal to. We are substituting this equation in. Substitute 2 in 1. Substitute a square. 9c square. C square is equal to 3b square. 3b square. B square is equal to 3c square. From this statement, we can say that 3 divides b square. Hence 3 divides b. Hence 3 divides b. Okay. Here we say that 3 divides a. Here we say that 3 divides b. From these statements, it can be said that a and b have a common factor 3, which is a contradiction to the previous statement. It is a contradiction to the previous statement, which is the previous statement. A and b are coprimes and root 3 is rational. So this is false. That statements are false because a and b have a common factor 3. Hence we can say that therefore root 3 is irrational. We proved that root 3 is not a rational number because a and b have common factor 3. Hence we can say that root 3 is irrational. Okay. Next question is show that 5 minus root 3 is irrational. Show that 5 minus root 3 is irrational. Here also the same method, proof by contradiction. Consider 5 minus 3. Suppose 5 minus root 3 is rational. 5 minus root 3 is rational. Consider two numbers a and b which are coprimes. Then we can rewrite a divided by b is equal to 5 minus root 3. Then we can say that 5 minus a by b is equal to root 3. 5 minus a by b is equal to root 3. We rewrite the equation. Bring two values. And here a and b are integers. A and b are integers. We already know that 5 minus a by b is rational. 5 minus a by b is rational. So 5 minus a by b is rational. Root 3 is rational. A and b are integers. 5 minus a by b is rational. So root 3 is rational. But this statement is a contradiction. We already know that root 3 is irrational. So this contradicts root 3 is irrational. This contradicts root 3. So this statement is false. We already know that root 3 is irrational. So this statement is false. If this statement is false, this also false. This is due to the incorrect assumption 5 minus root 3 is rational. 5 minus root 3 is rational. The value of b should not be equal to 0. Once again, we are going through. We have to prove that 5 minus root 3 is irrational. Here we are using the method proof by contradiction. Suppose or consider 5 minus root 3 is rational. Here we are representing 5 minus root 3 in the form of a by b, where a and b are coprimes. The value of b should not be equal to 0. Then a by b is equal to 5 minus root 3. We can rewrite the equation 5 minus a by b equal to root 3. Here a and b are integers, hence we can say that 5 minus a by b is rational. If 5 minus a by b is rational, root 3 is also rational. But we already know that root 3 is irrational. So this statement contradicts root 3 is irrational. So it contradicts root 3 is rational because of the incorrect assumption 5 minus root 3 is rational. Therefore, we can say that 5 minus root 3 is irrational. 5 minus root 3 is irrational. Let's go to the next question. 3 root 2 is irrational. Show that 3 root 2 is irrational. And also we are using the method proof by contradiction. Proof by contradiction. Consider 3 root 2 is rational. 3 root 2 is rational. We are representing 3 root 2 by using the integers a and b, which are coprime also, b not equal to 0. Okay, a divided by b is equal to 3 root 2. We can rewrite the equation as root 2 is equal to a divided by 3b. Then a divided by 3b is rational. A divided by 3b is rational. Therefore, root 2 is also rational. It contradicts this statement. It contradicts root 2 is irrational. It contradicts root 2 is irrational. So the assumption is false. A divided by 3b is rational. This statement is false. That is, it is a contradiction to root 2 is irrational. Hence this statement is also false. Hence we can say that 3 root 2 is irrational. The second last question, this one. 5 minus root 3 and 3 root 2 are proved as irrational by using the same method, proof by contradiction. Here we also take a by b. A by b is equal to 3 root 2. We rewrite the equation root 2 is equal to a divided by 3b. We are considering a divided by 3b is irrational because a and b are integers. A divided by 3b is rational. If a divided by 3b is rational, root 2 is also rational. So we state that root 2 is rational, but it is a contradiction statement to root 2 is irrational. We already proved that root 2 is irrational. So the preliminary assumptions are false. Therefore, we can say that 3 root 2 is irrational. So today we discussed about irrational numbers. What is an irrational number? What is an irrational number? And how to a theorem to prove many problems. We discussed that is the theorem is let p be a prime number. If p divides a square, then p divides a where a is a positive integer. This is the basic theorem to prove the further problems. Then we go through a lot of problems to show irrational numbers are irrational. So today class is over. Thank you. Thank you for watching. Thank you for watching. Subscribe and share for new videos.